Hey, what's up, guys? Chung here. So, so today let's take a look at another LeetCode problem here. Number 865, smallest subtree with all the deepest nodes. So this is another tree problem. So basically, you're given a binary tree, and you need to find basically the lowest ancestor for all the deepest nodes, right? So So how can we solve this problem, right? So first, I think it's kind of obvious that we need to find the deepest node first, right? And once we find the deepest node, we will be try to get the lowest root node for all deepest nodes, right? So to calculate the depth of a tree, we usually use a recursion, right? Basically, we get the left and right, right? And when we reach the leaf node, we return 0. Otherwise, every time when we have a left and right, we get the maximum depth from both between the left depth and right depth, and then we get the maximum and we plus 1, and then we return back to this one, right? So that's how we get for the current node, right? That's how we get the maximum node, the maximum depth for the left and the right. But now we need to add one more layer on top of that, right? Not only we need to get the depth for left and right, we also want to get the node, the tree node of the deepest node. So how can we do that, right? Basically, let's say we have a left and right. So we have a left depth and right depth here, right? So let's say we are at this like uh let's say we are at 2 here. The left depth is 1, right? The right depth is also sorry, it's also 1. It's also 1. And then basically our helper functions will return the depth of the current node plus the maximum depth plus the node of the deepest of the deepest leaves so far. So basically, if we have like 2 here, right? So the left and right they are the same, right? If they're the same, then we know, okay, so this the current node is our is our is the root node we need for the current depth, right? And then when it comes back to 5 here, right? When it comes to the 5, so the left side is 1 and the right side is 2, right? When it's not the same, right? So what do we do, right? If so, we get the root node from whichever side has the deeper depth, right? Because at this moment, right, on the right side, the tree node is still pointing at 2, right? And then we're at 5. Okay, so we're at 5. We see, okay, the right side has depth of 2, well, left side only has 1. So the depth is, of course, is 2 in this case, right? 2 plus 1. And but the tree node, we're still using the right side. And we only use the current node when the left side and right side are the same. Then we know, okay, so the current node can cover all the deepest leaf node. Okay, so I think that's the, and in the end, when we finish all the recursions, we simply return the second element from our recursion method. That will give us the at the root node, what's the what's the lowest what's the lowest uh, root node, right? Okay, let me try to code these things so that you guys can know a bit better here. So basically, I'm gonna have like a helper functions, right? Uh, this is gonna DFS, right? So node, right? So basically, if not node, right? If node is basically if it's a leaf node or it's nothing there, we simply return the 0 and none, right? Left depth equals to what? The DFS left DFS node left, right? And then right equals to DFS node right, right? So now we just need to compare, right? Basically, if the left, remember the first element of our return is the depth, and the second one is the node so far, is the current like the current result while we're at this node. That the current node that is the low which has the lowest common ancestor of all the leaves node, right? If left 0 is greater than right 0, right? And then we return what? We return the left 0 plus 1, that's the depth, right? And what? And the left 1, right? Else if left 0 is smaller than right 0, then we return the right side, right? The right 0 plus 1, and then right 1. And if they are the same, right? If they're the same, what do? We simply return any left or right. It doesn't really matter as the depth plus the current node, right? Because we know the current node has the common will cover it's a common ancestor of both left and right with the same length, same depth, right? And in the end, we simply return the DFS node, second one, right? So basically, we're using like we compared the left subtree's depth and the right subtree's depth depth, and we just use whichever is smaller. It's we use which side is has a bigger depth for both the depth and the common ancestor. And then let's just run it. Sorry, here it should be in root here. Yeah, cool. So all right, so I know this uh basically the idea here is that we are basically piggybacking on on the on the template of getting the biggest the biggest depth here, right? Because at this moment, you know, the zero, so the zero basically this zero will be the highest the biggest depth of the current sub uh of the current binary tree, right? And while we're calculating that, we're using the left side and the right side length to determine if we should use the current node as a result, or the or any of the child nodes. Mm, cool. I think that's it for this problem. Yeah, I hope I explain a little bit better for this problem. I know there's some other ways you can do it. I think one of the other ways it's more complicated. Basically, you find all the nodes has the biggest length here. I think here, um, like the first one is you find all the nodes with the deepest length, deepest depth, and then in the second approach, in the second loops, you just try to try to find the common ancestor of all the nodes that have the, the high the biggest depth. Uh, yeah, you can also do that. I think that way is like more intuitive, but I think it requires a bit more codings. And this way is like the most efficient way, but it requires you to make a little bit modifications on the existing uh, method, and you have to be aware of the how can you utilize the depth from both the left and right. Oops. Yeah, how can you utilize the depth from both left and right to determine which node you need to return, right? Cool. I think that's it for this problem. Yeah, thank you so much for watching the videos. Yeah, see you. Bye bye.